I'm Qianfan, and I will be presenting sample-based Matroid profit inequalities. This is a joint work with Hu, Pinyan, Zhihao, Hongxun, and Jinzhao. So let's start with a single item profit inequality. In this setting, there are several treasure chests for us, and each chest contains an item that its value follows some non-distributions. And at each step, we can inspect a chest and decide whether to take the item or not. And in this example, we decide to not take the first one, also not to take the second one, and we decide to take the third one. Since 6 seems to be high enough. And our goal is to maximize the expected accepted value. And we also want to compare that value to a profit's value, which since profit can see anything, profit will always get the maximum value. And in this realization, the profit will get a value of 8. And a classical result of single item profit inequality tells us that there exists an algorithm with value that's at least half of the profit's value. And the next natural question to ask would be, how about different feasibility constraints? Can we achieve similar performance with respect to different feasibility constraints, like what about I can select at most k items, or what about I can select a linearly independent set of vectors, or a set of edges that does not contain a cycle? It turns out that all these constraints are special type of Matroid. So let's take a look at so-called Matroid profit inequalities, where we are further given a family of feasible sets that is a Matroid. And now, when we are trying to select items, we need to make sure that the set of accepted items is always inside this feasibility family. And our goal now is to maximize the sum of accepted values. A celebrated result by Kleinberg and Weinberg 12 years ago says that in this setting, although it seems like much more difficult than a single item, but we can achieve the same guarantee. And also, this type of profit inequalities has many applications to auctions and other mechanism design, other mechanisms. But in these settings, often only samples to those value distributions are available. So this makes us wonder whether if the full information of distributions are not available, but we only have sample access to those distributions, can we get a similar performance guarantee? Specifically, in this sample-based profit inequality setting, we're given k independent samples from each distributions. And we want to ask what's the best we can do. And there are rich line of work in related settings. Specifically, a lot of work are focusing in the single sample case, which is saying that if only a single sample from each distribution is available, what's the best we can do? And very surprisingly, for the single item profit inequality, we can actually achieve the optimal via single sample. And there are also other works on special matroids or matchings, etc. But what is so special about the problem that we want to study, the sample-based Matroid profit inequalities? One thing to note here is that it has a very close connection to the well-known secretary problem, which is a problem that's very similar to profit inequality. However, the values there are chosen adversarially, but items will arrive in a uniformly random order. And in the field of online algorithm design, it's a long-standing open question that whether there exists a constant competitive secretary algorithm for general matroids. So previously, we already know that if we have a secretary algorithm, then via a reduction, so this does not hold for every algorithm, but for most secretary algorithm, via a reduction, we can derive a single sample profit inequality for the same feasibility constraint. And actually, in many previous work on single sample profit inequality, is using this reduction. However, very recently, another direction is also discovered for, also proved for Matroids only. And this means that if we derive a constant compatible Matroid profit inequality with constant number of samples, then we will resolve the Matroid secretary conjecture. And we didn't though. So here are several existing results for the setting of sample-based Matroid profit inequalities. So we already know that the optimal ratio of half is achievable in the full information setting. And if we restrict the number of samples to 1, then we know that the only thing we know is via that reduction that we just mentioned, there is a 1/O of log rank competitive Matroid profit inequalities. So there's one thing in the middle that we know, that is via so-called online contention resolution schemes, we can achieve competitive ratio of 1/4 using polynomially many samples. And our result says that, well, actually, we only need to use polylogarithmic many samples to achieve the similar guarantee. And our method is based on a quantile-based threshold strategy plus OCRS. So this is our whole framework of the paper. So first, we derive nearly 1/4 selectable Matroid OCRS with polylog samples. Then, via reduction from Matroid profit inequality to OCRS, which also use log n samples, we derive the 1/4 selectable Matroid profit inequality with polylog samples. Now let's first start from the most classical threshold strategies for single item profit inequality. And the idea is to set some fixed strategy, T, and upon each arrival of items, we accept these items if and only if their values is greater than the threshold T. And it is known that we can use median-based thresholds, which is simply the median of the maximum value over these items. The problem with this type of method is that we don't really know how to generalize those median-based thresholds to the Matroid setting. Another way to use a threshold strategy is via expectation-based strategy, where this is exactly what Kleinberg and Weinberg did in their Matroid profit inequality. And they said, so their method, if applied to single item case, will be the threshold would be the half of the expected value of the maximum. However, if we want to generalize this expectation-based method to general Matroid, a crucial issue here is that we cannot estimate the expected value efficiently using any finite number of samples because the distribution here is unbounded. So there might be a very large value with an extremely small probability, and we have no chance seeing that. So our plan is to starting from the medium-based strategy and try to generalize it, this strategy to the Matroid setting. So here is a more specific description. So in Matroid, we will definitely want to use first based on some value called tau I, which is defined as the minimum weight for each element I to being opt. And this is a well-defined quantity, which also only depends on other values. And that's our threshold strategy is very simple. We call item I to be active whenever this value is greater than this threshold, which is the median of such tau I. And the good thing about this threshold is that it's easy to estimate by log samples in the quantile space, I mean. And ideally, we want to accept every active items, but that is impossible because the active set might not be feasible. Even if we ignore that issue, there's another issue about the optimality. That is, even if we can accept the whole every item that is active, we still need to show that this indeed will approximate the optimal set. For example, this is a half approximation. And to solve the first issue, we will use OCRS. And the second is actually a non-issue for this specific threshold. And we will prove this using a global argument. So why? So here, I'm not going to cover the whole argument because it's kind of involved. But let me mention that why local argument fails. So formally, a local arguments are the most simplest arguments that we want to make. That's if we want to argue that the set of active items can approximate the optimal set. Ideally, we want to argue that the contribution of each item can approximate the contribution of that item to opt. But that is impossible in this setting because let's consider a K-uniform matrix where the tau I is basically the K's largest value here. And according to our algorithm, we will set a single threshold T for all I. And we have two possibilities. One possibility is that we have the K's largest value greater than T. One is smaller than T. And both of them happens with probability half because we're choosing the median of K's largest value. However, consider an item J with a deterministic value Bj slightly smaller than the threshold we set. Note that this item will be in optimal set with probability nearly half. However, so it has significant contribution to the optimal value. However, since its value is deterministically smaller than T, it's never active. So it's hopeless for us to find such a local argument in this setting, even in the K-uniform matrix setting. So for general matrix, our proof is by using a benchmark that is the maximum basis for all threshold values. And we argue that the contribution of active elements to opt is greater than this benchmark. However, the contribution of inactive elements to opt is smaller than it. Therefore, this leads to a half approximation. And the key to it is weighted strong basic exchange lemma from some modular maximization literature. And also, our actual strategy at last is actually by using multiple quantiles instead of a single medium to improve the competitive ratio. Okay, so we have solved that issue, but still, let's go back to the feasibility issue that we didn't solve. For the feasibility issue, now let's say that now each item is active with some probability pi. And a good fact here is that actually these probabilities are feasible, ex ante feasible. And formally, we say that the probability vector approximately lies in the Matroid polytope. Then, if we were in the full information setting, then we can use the online contention resolution schemes to approximate the active set to a feasible set by losing a factor of 4, since we know that there exists a 1/4 selectable OCRS for matroids. So the only thing left for us is to make this OCRS work in the sample-based setting. And that turns out to be a very non-trivial task. So let's take a look at the only place in their construction that use the samples. So basically, the idea is that we want to select, we want to protect some elements who are easily spanned by other active elements. For example, in this graphical matrix, we will realize that this 2 dotted edge the top dotted, the top dashed edge is easily spanned by others. So we will protect this edge. And the bottom one, after this protection, becomes also fragile to others. So we will also protect the bottom edge. In this way, the output of this protect subroutine would be these two purple edges. And so our task is simple. We only need to derive a sample-based version of this subroutine, which seems to be a simple task because there is only a polynomially many queries to in the form of this probability, which we should be able to estimate it efficiently because by Chernoff bound and union bound. However, this is not true because these queries are highly adaptive. So when true answer lies very close to the parameter C, whether we update this protection set S really depends on the error. So there are actually exponentially many queries that's possible. And we can definitely not use union bound. So since we're running out of time, I will briefly sketch what is our idea for solving this, for turning this procedure to a sample-based one. So we observe that although for the two sample-based version of the protection set, although there will always be some items that's problematic, but they are disjoint. So the only thing we need to do is to randomize over these two sets and two parameters. In this way, every item fails with probability only at most a half. And finally, since this subroutine would be called multiple times, so we actually need the failing probability to be at most 1 over log n, and which results of a log n to the 4 samples in total. Okay, quick summary, our result, sample-based OCRS and the reduction based on quantile threshold from profit inequality, from Matroid profit inequality to Matroid OCRS. And we get the sample-based Matroid profit inequality. And there are several open questions. So first, definitely, since everything here is not tied, basically everything has possibility to be improved. And the grand prize is definitely to derive Matroid profit inequality with constant samples, and of course, constant selectability. That would resolve the Matroid secretary conjecture. And that's it.